Hi all. Let me introduce myself first. I am Manoj Khandelwal. I am an associate professor and the program coordinator of mining engineering at Federation University, Australia. I did my bachelor's in mining engineering and master's in rock mechanics and then later on PhD in rock engineering. I was an assistant professor at Maharana Pratap University of Agriculture and Technology in India since 2007 to 2015, and then later on I joined Federation University, Australia in 2015 and currently working there. And the today's presentation, okay, and the today's presentation is related to artificial neural network based prediction of blast vibrations for mining and civil infrastructure applications. Blasting is one of the most, you can say, widely used techniques in mining along with infrastructure engineering or civil engineering, we can say. And it is, you can say, whenever we can say blasting is performed, it is definitely accompanied by, you can say, different type of blast nuisances like blast vibrations can be there, air blast can be there, and which significantly affect the surrounding structures' health, along with their environment and nearby communities. So, the understanding of mechanism of vibrations generations, their propagations through you can say, different geological media and their potential impacts is essential to design a safer and more efficient blasting operations. So in this presentation, I'll be discussing consider the evolution of consider vibration characteristics from experimental and field trials or data. I will be also exploring consider different predictor approaches or different predictor equations, consider their evaluations. Along with, we will be also discussing about machine learning models, and we will also highlight consider their significance in controlling blast vibrations but at the same time ensuring operational efficiency and community safety. Okay, so explosive, these are still remain the cheapest and fastest available source of energy for the excavations in any hard rock mass. Of course, in soils because we don't need any, you can say, blasting or explosives. In of course hard rock, definitely explosives are required, and these are the cheapest one. And in large scale mining or civil infrastructure projects, definitely the ability of explosive is is to consider instantly or immediately release very high concentrated amount of energy. And due to that, we get fragmentation along with displacement of hard rock mass from their parental positions. And even though different significant advances have taken place in mechanical excavation technologies, but still no other economical and practical source of concentrated energy has been developed that can replace explosives to achieve the same efficiency in fragmentation and displacement. And even over the decades, significant progress has been taken in explosive formulations, initiation systems, along with blast design techniques, and which generally results in safer, more reliable, and more controlling blasting operations. However, one of the most considered major challenges that still persists in the relatively low efficiency of energy utilization. And hardly a small fraction of energy we are able to use in fragmentation and displacement. And a significant amount of that energy which we get from explosive detonation just completely goes into or mix into the environment and create number of different type of blast nuisances. In terms of, we can see ground vibrations can be there, air blast can be there, fly rocks, heat, noise, such type of things are there. Okay, and just only as I told you, just hardly we are able to use 20 to 30% of this explosive energy. And as per energy principles, we know that energy that cannot be destroyed, just from one form to the other form we can convert it. So when we are saying 20 to 30% of energy we are able to use, definitely the rest 70 to 80% explosive energy is there, which we are not able to use, but which the energy will be there, and that energy creates number of different type of ill effects. In terms of significant, you can say impact is there related to ground vibrations, pyro can be there, air blast can be there, back breaks, noise, but among them ground vibration is the most challenging thing. The reason, because whenever you can say highly populated areas are there, or any civil infrastructure projects are there, you can say when we want to make high rise buildings, definitely for that we need strong or solid foundation should be there, and to get that definitely blasting will be required. And so whenever you can say any such type of issues are there, definitely ground vibration is a major concern, because the people living surrounding to that, their dwellings may get damaged, or may you can say get some such type of, you can say, cracks or other type of problems may occur. And blasting, it is really a very complex phenomena, and influenced by, you can say, different parameters are there, but we can categorize them into three segment major, you can say, components. One is explosive parameters. We can say in that what type of explosive we are using, whether it is high energy explosive is there, low energy explosive is there, how much velocity of detonation is there, and how much density is there. Second one is blast design parameters, which as I can say blast engineer that is in control, which any blast engineer can control. That is what parameters are there in that. That is how much burden is there, spacing is there, stemming is there, charge length is there, along with what type of delay they are using, initiation pattern is there, all such type of things are there, that are, you can say, controllable parameters. And the third and last rock parameters are there, that what type of strength is there, elastic properties are there, such type of things are there. So among that, you can say in these three explosive parameters, once we have decided any explosive, it's not possible to change again and again explosive. Rock parameters, that is again beyond our control, because that is natural things are there. So as a blast engineer, only blast design parameters are there, which by which we can play, and we can change or modify or accommodate blast requirements, or we can optimize that. Okay, now here we can see ground vibrations. Let's see here in this image, whenever any explosives are detonated here, in that, consider just as we are saying, just hardly 20 to 30% explosive energy we are able to use. So in that, what happens? Because all this happens instantaneously within a fraction of seconds. So whenever an explosive charge detonates, a tremendous amount of energy in terms of very, very high temperature, that can be near about more than 5000 degree kelvins, and very high pressure that can be near about more than 10 to 20 gigapascal, just liberates. And it all happens within a fraction of second. And due to that, some elastic and inelastic processes starts. Inelastic process means plastic deformation surrounding to the blast hole wherever we are performing blasting operation. So near about 20 to 50 times of that blast hole diameter surrounding to that, you can say, plastic deformation will be there. Beyond that, the energy which is still there but which is not high or significant enough to break or to make cracks in the rock mass, but that will be there, and that creates elastic effects, and that elastic effects are generated in terms of these blast vibrations or ground vibrations, we can say. And in that, we generally have two different type of waves. One is body wave, which travels through a body, and the second one is surface waves, which travels through the surface. So once any body wave is there, it will reflect like that, and once it has reached to surface, it will become a surface wave. So in that body waves, we can say P wave or S waves are there. So P wave is a mostly, you can say, their propagation is, you can say, compression or dilation. It makes like this image A, we can see the impact will be like that. Shear wave, that can be horizontal or vertical, you can see shearing can be there, and in that we can see how much B and C impact is there. Surface wave, their motion is pretty much very similar, like, you can say, whenever you can say any wheel rotates, so retrograde motion is there. And among these, surface waves are the most dangerous for any surface structures. Okay, now if we are talking about ground vibrations, different parameters are there in that. geological properties are there, what type of geotechnical properties are there of that particular area or region, geological discontinuities in that, we can say fault, you can say any unconformity or anything is there that comes into that. Then other thing is that distance, wherever we are performing blasting operation, along with where our location or any structures location is there, how much distance is there, that will also very significant. Then what type of blast design parameters we are using in that, that is, as I told you, burden, spacing, such type of parameters are there, definitely that is very important, along with how much explosive we are using with respect to single delay. Then whether waters or hydrological or dry area is there or water is present. Then what type of rock is there, whether it is sedimentary rock is there, igneous is there, or metamorphic rock is there. Then what type of explosive, whether it is high explosive or low explosive is there. So all these things are there which affect ground vibrations significantly. Now thing is that why we should know about blast vibrations. The reason, because we want to make excavation process more efficient and can say responsible. And in that, definitely, what is our can say thing is that we want to make economical. Anything we are performing, definitely money is very important. So any operation we are doing, that is economical. We want to optimize blast design, and so that we can reduce or minimize explosive wastage by anyhow. So that definitely we will have to use lesser quantity of explosive. Along with, we want to minimize damage to the surrounding rock mass. Along with, say any equipments are there or any structures, definitely we want to minimize in any impact on that. Then safe and stable blasting operation we want to perform. In that, what we can say, definitely want to control ground vibrations so that any structural damage is there which we can definitely avoid or minimize in that. Definitely in that, fly rocks, then back breaks or noise, or you can say, or air blast or such type of things, definitely want to avoid. Along with, we want to perform eco-friendly blasting. Eco-friendly blasting means definitely all such type of nuisances we want to avoid, or such type of environmental footprints and disturbances to local habitants, we want to avoid that. Then sustainable infrastructure development, we want to that, in that we can say we want to perform responsible, or we are performing, or we want to promote responsible use of any resources so that we can reduce their adverse or negative impacts, and we can also perform or make sure long-term operational stability, and so that we can compliance with the regulatory standards or body. Now in that, what is that knowledge exists, first thing is that what type of knowledge currently we have. Definitely different type of vibration predictors are available based on empirical relations. But in that, what is the issue? All the predictor equations are there. They are mostly based on 2 or 3 different parameters. Now, what those parameters are there? First is how much explosive charge is there with respect to single delay. Then second one, most critical, that is how much distance is there from your blast location to your monitoring point. So these two parameters are the most significant, and all the equations or these predictors are based on that. Along with, a few researchers have also used some attenuation factor that is based on rock mass characteristics. So this, but the issue is that different predictors are there suggested by different researchers, but if we want to use all of them, we can see huge variations or will be there, whether we should use this one or the other one. Of course, we will be discussing that later on. And due to that, sorry, okay, other than that, whenever you can say vibration, we are talking frequency is another thing which is very, very significant, but none, you can say no, these predictor equations are there by which we can know about the frequency. Very simple thing is there, if any, you can say vibration level is there, let's say you can say 5 millimeter per second is vibration level is there, but one with very high frequency, the other one is with very low frequency. Definitely high frequency vibrations, you can say, are very easy to manage compared to low frequency vibrations. But we do not have any, you can say, mechanism by which we can know how much vibration, how much frequency will be there. And as I mentioned or told, just only 2 to 3 parameters are there by which all these vibration predictors are based on. But as we discussed, you can say blasting or vibrations depends on rock and blast design parameters which we do not incorporate in any of these conventional predictor equations. Okay, so for that, what we did, we have just performed this study so that we want to evaluate the different vibration predictor equations efficiency, whether they are really able to predict the vibration level in an efficient manner or not. The second thing is that, as we mentioned, different parameters are there which influence blasting operations along with vibrations, so that we want to also know how much real weightage is there with respect to each of those parameters. Along with, because when we are saying blasting is there, definitely we want to protect any infrastructural project surrounding to that particular mine or area, so that we can know, okay, how much vibration level that structure can sustain, and we need to make sure that whatever explosive we are using, that should generate the vibration level below the threshold level which that structure can bear. So we want to know the explosive charge or the safe charge for that particular structure. Okay, so for this, what we did, we just performed this study at Singrauli area, which is located in India, and which is also known as coal capital of India. And number of different coal mines are there in that, and which is very very sensitive, because all these mines are surrounded by local different residential areas are there, and they always face such type of issues. So and that area, the Singrauli area, different mines are there in that. They generally, you can say, in many mines they have large drag lines, and due to that their bench height is near about 40 to 45 meters are very easily they have. So here we can see different blasting terminology, that burden is there, that is minimum distance from the blast free phase to the first row of holes. Then how much streaming, that is inert material is there, how much explosive charge is there, which is, you can say, explosive that will detonate, and due to that we get energy. Along with sub drilling, is that is extra additional drilling we need to perform so that we can remove the tow burden. And booster is there, so that is very high energy explosive is there. So because of detonation of that, this explosive charge that will detonate. And here we can see burden spacing near about 9 meters and 11 meters are there, and multiple rows can be there in that, and in one row multiple holes can also be there. So for that, what we did, we monitored 175 blast vibration records from that area at different locations. And you can see here this table, it shows number of different equations. So you can see seven equations are there suggested by different researchers. In that we can see D is distance from blast location to your monitoring point. Q max is how much explosive charge is there with respect to single delay. K and B are the site constants values are there, and V is peak particle velocity, that is blast vibration level we can see. Along with, you can say, alpha is also there, that is, you can say, used by Gauss-Dayman equation. But here we can see only 2 to 3 parameters are there, not all the, you can say, influencing parameters are there. Okay, so here we have used machine learning, artificial neural network. So what we did, their ANN or artificial neural network completely works as like a human neural system, because whatever things we learn, that is based on by watching or by listening or by doing. Same thing here also, the same thing is there. We provide some input parameters along with their corresponding output parameters, and based on that, this ANN makes certain relationship among them. Okay, so in that, learning training phase is there, and then testing phase is there. So here we can see 3-layer feed forward back propagation neural network is there. So initially what we did, whatever values 100, as I mentioned, 175 blast vibration records we did. In that, 150 blast vibration records were used to train this network. So for that, input parameters, these 13 parameters are there which we use for this study. In that, explosive parameters, blast design parameters, and rock parameters we use along with their corresponding peak particle velocity and frequency. Whatever we got, we just give that to that artificial neural network to train the network. Based on that, it made certain rules, regulations, and it is, you can say, iterative process is there. Until unless, you can say, this network trains by themselves, you can say iteration process will go on until, you can say, this user defined error is not reached. Okay, now how we can evaluate for that? in that the rest 25 data for which we have output values, but we didn't provide to the network for this ANN, so that we can cross check whether whatever you can say outcome it is producing better, that is close to the actual output or not. So 150 data sets were used to train the network, and the rest 25 data sets we use to just test the network. Here we can see 13 different parameters. So these yellow ones are blast design parameters, these blue are rock parameters, and the rest two, that is number 12 and 13 explosive parameters are there. And here peak particle velocity and frequency range is given for 175 blast vibration records, along with all these rock parameters, explosive parameters, and blast design parameters. Okay, now what we did, because we have different, you can say, equations were there, so we just use, as I mentioned, 150 data to train the network. So here we can see in prediction for this 25 rest data sets for PPV and frequency, we were getting nearly, you can say, more than 95% confidence level. Just you can see this is one slope line is there, and all the data sets are just coming close to each, you can say, that one slope line. Same thing we just perform multivariate regression analysis as well for these 13 parameters based on least square method. So based on that, we got these two equations, PPV and frequency. The same equations were used for the same 25 data sets, but here we can see huge scattering is there for this prediction values for PPV along with frequency. And even though 13 parameters were used for the NN modeling, same thing, same 25 parameters were used for this multivariate regression analysis modeling, but here we didn't get proper outcome. And here you can see, compared to one slope line, data sets are completely scattering here and there. Same thing we did, 150 data sets were used to get the site constants value of different equations. So here we can see the first image by which we got site constants value, and second image you can see prediction and measured values of peak particle velocity. Here also we can see from one slope line, the values, prediction values are going completely or completely deviating from here. Same thing we can see with Ambrasi-Hendon equation. Similarly, Langfors-Killstrom equation also showing the same trend. Indian standard predictor also showing the same trend. We can see here all the data sets are completely scattering. Same thing is happening for general predictor equations. Along with Gauss-Diamond equation, two different equations are there which we use. Here also we are getting the same trend. Along other, can say, CMRA predictor is there which we also use. Here also pretty much very similar trend is there. Okay, now this chart or graph shows sensitivity analysis. Here we can see or just to find out which parameters really influence the blast vibration level or frequency. Here also we can see definitely explosive charge with respect to single delay and distance. These two have the most significant influence on PPV and frequency, but still other parameters do have, can say, influence on blast vibration level, but any of the conventional predictor equations do not use or do not, can say, incorporate these values. Here comparative chart we can see, that is measured values of peak particle velocities are just very close to the NN prediction values compared to any other, you can say, predictor equations along with MVRA values. Same thing, because for frequency we do not have any conventional methods to predict frequency, and due to that just ANN, MVRA, multivariate regression analysis, and measured frequency values are there. So here also we can see the same trend that ANN values, prediction values are very much closer to the measured frequency values, whereas MVRA values are completely going here and there, even no close to the measured frequency values. Okay, and as I mentioned, why do we want to perform this study? So that we can find how much safe charge is there for that. And here also we can see that is related to structure is located 200 meter distance away, and how much explosive charge we can use. So that here we can see some of the, say, equations are showing very high intensity explosive charge, whereas some are showing very low explosive charge. So that is means we do not have any consistency by using all these equations, and we do not know whether we should use USBM equation or CMRA equation or any other thing. Okay, based on this study, we can say that, of course, machine learning techniques are very efficient because they do not bound based on linear equations or logarithmic equations. Such type of things are there, and by which definitely we can get proper outcome. And such type of techniques or tools can be used in such type of models where non-linear relations exist to get proper outcome. That is all about this. Thank you very much.